Sheaf semantics of termination-insensitive noninterference. I'm John Sterling, and this is joint work with Bob Harper. Computer programs frequently must deal with sensitive data. That includes your passwords, your browser history, your bank account number, or your identity as a referee of a journal paper. The goal of information flow control is to provide tools to control the leakage of such data through program outputs. Noninterference is a property that measures what kind of outputs can depend on what kind of inputs. The state-of-the-art in type-based information flow control is extrinsic relational semantics that impose noninterference properties on an existing insecure model of computation, such as domains or operational semantics. Our contribution is a new intrinsic denotational semantics for information flow control based on the open and closed modalities of topos theory. We will now describe how to achieve noninterference using closed modalities. We start with a meet semilattice P to be thought of as the collection of security clearances. For instance, P might have low, medium, high, and top security clearance. We can turn P into a space or a topos by taking presheaves on it. We will call the resulting space P as well. Let us explore the space P as a setting for developing a synthetic theory of security and redaction. An open, phi, of the space P is then a formal join of security clearances. We might refer to this as a security policy. Meanwhile, a sheaf on the space P, which is just a presheaf on the original meet semilattice, is a structure that has extent over each security policy phi. The restriction of a sheaf A to a security policy phi is then the part of A that is visible under the policy phi. In particular, the restriction of A to the medium security policy is the part of A that is visible to both medium and low security observers. For each security policy phi, we have a pair of complementary open and closed subspaces. It is instructive to think synthetically about the security policy phi. In the language of sheaves on P, phi is a proposition. Thus, a sheaf on the open subspace is an object that thinks phi is true, whereas a sheaf on the closed subspace is an object that thinks phi is false. A sheaf on the closed subspace can alternatively be characterized as one whose restriction to the open subspace is trivial. We will now visualize the modal operators corresponding to these subspaces and their application to security. We may visualize a sheaf A as a pill with components corresponding to what is visible at each security clearance. Restricting to the open subspace determined by the medium security clearance, we have a truncated pill that contains only the data visible at the medium and low security clearances. Restriction was the inverse image part of the open immersion from the medium security truncation to the entire space. The direct image functor, which is right adjoint to inverse image, extends our truncated pill as follows. It fills in the missing data by the limit of the data that it had. Thus, what is visible at high security is now only what was visible at medium security in the past. The round trip, going from the entire space to the truncation to the medium security clearance and back to the entire space, is then the open modality for the representable proposition corresponding to the medium security clearance. If we view the medium security clearance as one of our pills, it has empty extent in the top and high security clearances and trivial extent in the medium and low security clearances. Thus, it is not difficult to show that the open modality can be computed by the exponential. The open modality should be thought of as purging high security data and replacing it with the limit of low security data. Analogous to the open subspace, the closed subspace generates a closed modality. Whereas the open modality replaces what was visible to high security clients with the limit of the low security data, the closed modality leaves the high security component alone, but zeroes out the low security component. This has the effect of ensuring that a low security client can never see the data. In particular, if we start with a sheaf A viewed as one of our pills, we restrict it first to the closed subspace. This means simply removing the bottom two components. We then extend it to the entire space by filling in the missing data with the point. This object can also be computed as the pushout of the two product projections determined by the medium security clearance and A itself. We can now analyze the applications of the closed modality to security. We will imagine a programming language whose types are interpreted as sheaves on the space P. Then a higher security type is a sheaf on a closed subspace, or alternatively, it is a sheaf that lies in the essential image of the closed modality. Imagine that we would like to have a type of integers that cannot leak to medium or low security clients. We may seal the sheaf of integers under the closed modality for the medium security level. As far as high security clients are concerned, that is, types that are in the image of the closed modality, the sealed integers are the same as the ordinary integers. They can always read the data, but low security clients will be unable to read the data. We may now prove a semantic non-interference result concerning the sealing of a given type A at the medium security level. In particular, any function from the sealing of A into the Booleans is constant. This follows immediately from the fact that the type of Booleans viewed as a sheaf is constant. Next, we examine how to extend our account of non-interference and information flow control to account for partiality. In the field of programming languages, we are mainly interested in languages that support partial functions and general recursion. In semantics, partiality means that we have a dominance, that is, a classifier for a collection of monomorphisms or subobjects that will serve as the supports of partial functions. The partial map classifier can be computed as a partial product of the dominance itself. Thus, a partial function from C into the lift of A, or the partial map classifier of A, is determined uniquely by a total function U arrow A defined on a sigma admissible subobject, U of C. In the presence of partiality, there are at least two different kinds of non-interference that we could consider, corresponding to the two different ways to think of a partial function as a total function. On the one hand, total, or termination-sensitive non-interference, states that any function from a sealed type into the lift of the Booleans is constant. On the other hand, partial, or termination-insensitive non-interference, states that any function from a sealed type into the Booleans is constant. Thus, under the partial non-interference regime, if we have a partial function from a sealed type into the Booleans, then it might be that this partial function decides whether or not to terminate, depending on sealed inputs. On the other hand, when it does terminate, it always produces the same value regardless of its input. In the classic relational or extrinsic semantics of non-interference, termination-insensitivity has been difficult to capture, with the existing models having a number of disadvantages. In our setting, on the other hand, the termination-insensitive non-interference is the natural notion. Indeed, termination-insensitivity follows immediately from standard domain-theoretic semantics, if we do that domain theory internal to sheaves on P. Developing domain-theoretic semantics is daunting enough without having to do it in sheaves. A simpler approach is given by synthetic domain theory. Synthetic domain theory is like a special kind of set theory that has recursion built in. At a more technical level, synthetic domain theory is the internal language of a topos, equipped with a dominance that satisfies certain important properties. In a topos model of synthetic domain theory, a predomain can be defined by a simple orthogonality condition that abstracts the closure under colimits of omega chains. Then a domain is defined to be a predomain that is equipped with the structure of an algebra for the lifting or partial map classifier monad determined by the dominance. There are two main ways to construct topoi that model synthetic domain theory: realizability and sheaves. We'll focus on sheaf models. Fiore and Plotkin have shown how to take an existing category of predomains, such as the category of omega CPOs, and construct a Grothendieck topos model of synthetic domain theory into which the original category of predomains embeds fully faithfully, such that the dominance on the topos extends the original notion of Scott open subspace. One of the main technical contributions of our paper is to extend the recipe of Fiore and Plotkin to apply when the base topos is a different Grothendieck topos than set. In particular, if we take P as our base topos, we obtain a topos model of synthetic domain theory D equipped with a geometric morphism into P, such that the dominance on D is exactly the inverse image of the subobject classifier of P under this geometric morphism. Put more humbly, we obtain a model of synthetic domain theory in which the termination supports for partial functions can depend on security levels. In particular, the resulting notion of partial map includes not only convergence and divergence, but also divergence above a certain security level. There are computations that appear to converge for low security clients, but which can be seen to diverge for high security clients. The resulting security-sensitive synthetic domain theory exhibits a form of declassification. Let A be a sealed type. Note that it is not the case that the type of computations of type A, or partial elements of type A, remains sealed. That's because a partial element of type A carries the data of its termination support, and that's not sealed. Nonetheless, we may define a function that declassifies a sealed partial element of a sealed type. For high-security clients, the behavior of the declassification of a sealed partial element is the same as the underlying partial element. But for low-security clients, the declassified partial element always converges, regardless of whether the original converged. From an operational or dynamical perspective, the declassification operation can be seen to be a form of parallel computation. In particular, the element of the dominance corresponding to the medium security clearance can be seen as a computation or an assertion that converges whenever we are restricted within the medium security clearance, and diverges elsewhere. The declassification operation runs this assertion in parallel with the original underlying partial element. So far, we've given a denotational semantics for a programming language with modalities for security. In this denotational semantics, we have a desirable termination-insensitive noninterference property. But what about in the programming language itself? The relationship between the intrinsic equational theory of a programming language and the equational theory induced by a denotational semantics is governed by Plotkin's adequacy lemma. Adequacy implies that denotational equivalence is a subrelation of observational equivalence. Thus, adequacy is exactly what is needed to deduce a syntactic noninterference result up to observational equivalence from our existing denotational semantic noninterference result. We can easily prove the adequacy lemma using synthetic Tate computability, which is a synthetic version of logical relations based on the internal language of Artin gluings. The exact instantiation of synthetic Tate computability that we will use to prove adequacy is as follows. We extend the internal language of a topos with two disjoint propositions corresponding to syntax and semantics. The proposition phi syn determines an open subtopos corresponding to syntax, and the proposition phi sem determines a disjoint open subtopos corresponding to semantics. Then we axiomatize the data of a generic or arbitrary model of the programming language within the syntactic subtopos. Then, we add the axioms of our security-sensitive synthetic domain theory to the semantic subtopos, along with an extra axiom that establishes the correct relationship between the semantic and the syntactic security clearances. In the semantic subtopos, we may replay the denotational semantics that we gave before. Now we have two models of our programming language. We have a syntactic model in the syntactic subtopos, and we have a semantic model in the semantic subtopos. A logical relation between these two models is then a third model of the programming language that takes place in the entire topos, with the additional property that it restricts within the syntactic subtopos to the syntactic model, and it restricts within the semantic subtopos to the semantic model. By constructing such a synthetic logical relation, we verify the Plotkin adequacy lemma, and obtain as a corollary the partial or termination-insensitive noninterference result for the original programming language up to observational equivalence. To summarize, we have contributed an intrinsic denotational semantics for termination-insensitive noninterference, an alternative to the usual extrinsic or relational accounts of noninterference that seems better adapted to termination insensitivity. As a side contribution, we have shown how to extend synthetic methods such as synthetic domain theory and synthetic Tate computability to prove non-trivial results about complex programming languages that combine security modalities with general recursion. Thanks for your interest and attention.